Okay, welcome to this video, the second in our series of videos covering the syllabus. This is instead of classroom, so we will have time to do some past papers in the lesson. Okay, so this one is on carbonyl compounds, aldehydes and ketones, and we're going to try and get through as much of this as we can. This might take two videos, in fact. Okay, so there's the syllabus. You can have a quick look. And first of all, we're going to have to define what a carbonyl compound is. So carbonyl compounds. Okay, so the first thing we've got to know about them is they have this grouping. This is called the carbonyl group. Okay, now depending on where the carbonyl group is in the molecule, it's either an aldehyde or a ketone. Okay, now if it's an aldehyde, the carbonyl group is at the end. We say it is terminal. Okay, so there, the carbonyl group is at the end of the molecule. And if it's a ketone, the carbonyl group is somewhere in the middle. So there we are. So these two are isomers of each other. And if they have the same number of carbon atoms, aldehydes and ketones will be isomers. So they're isomers of each other. So you have to look out for that. Right, so you can see the carbonyl group on the left is at the end. There we are. This is terminal. Terminal just means at the end. And this one is kind of central. All right, so how would we write this down? Get a nice color here. Oh, I've got that one already. Let me use not red, blue. Okay, aldehydes are shown like this as a general formula, whereas ketones are shown like that. Whereas where the little dash of the prime thing means the alkyl group might be the same or it might be different. Okay, so there you go. These are the two carbonyl compounds that we study. Right, now, before we go on, let's have a look. What's the first thing? We have to the oxidation of primary alcohols using potassium manganate or acidified potassium dichromate and distillation to produce the aldehyde. So we've done these already in class, but let me show you. Let's start off, let's get rid of this color. Let's start off with my primary alcohol, and I'm going to start off with propanol, propan-1-ol. So this is propan-1-ol. And I'm going to oxidize it with one of two things. Excuse me. I'm going to oxidize it. Let's use it's orange, isn't it? Potassium dichromate, and we acidify that, and we heat. Or I could have used the purple stuff, potassium manganate, again, acidified, and heat. Okay. Now, if we oxidize primary alcohol, we get the corresponding aldehyde. So let me grab the aldehyde, this one. And so if we do propan-1-ol, we'll get the corresponding aldehyde, which is propanal. Okay, there's propanal, and there's the aldehyde group. Now, as you all know, the color changes on this one. This top one, this potassium dichromate, would go from orange to green. And the bottom one goes from purple to colorless. Okay, and we have oxidized our propanol. All right, to propanal. Now, what would we use? We'd use for this one, let me try and get a nice red pen. We would use distillation because we want to go from the alcohol to the aldehyde without going to the carboxylic acid. So we use distillation to capture my aldehyde before it gets to the carboxylic acid. So we'd use distillation here. All right, I think that's everything. Oh yeah, before we go on, let me get another color here, a nice white color. How would you write this in an exam if you had to do the balanced equation? Well, it would be CH3, CH2, CH2, OH. This is my propanol. And I gain one oxygen from the oxidizing agent. This is how we do it. Okay, it gives us CH3, CH2, CHO, and we get water. So this is the equation. And where does this oxygen come from? This is from the oxidizing agent. Okay, we don't have to know oxidizing agent. We don't have to know how it gets off the oxidizing agent. It just does. Okay, and there's my aldehyde. So the first way we make an aldehyde, or according to this anyway, the syllabus, is we oxidize an alcohol. Now, how do we make a ketone? Well, let's go for that one again, that colour. Ketone, I use a secondary alcohol. We've done this in class. Oh, that's not an alcohol, is it? We use a secondary alcohol. There we go. Okay. And we oxidize this. And we get, and if we do this, oops, I've got two whites there. So if we do this, we get the ketone. Like that. And water. Okay. How would we do it? Same as before. We would use potassium dichromate, acidified, and we use potassium manganate, acidified, okay, H plus, and heat for both of them. And we use, it doesn't matter what we use here because this isn't going to further oxidize. So if you're chasing after a ketone, you can just use distillation or reflux distillation because it's not going to further oxidize. It's not going to change this to something else. So that's how we oxidize primary alcohols and secondary alcohols. So let's go back into the syllabus, make sure we're on track. So we've done this one, yeah, and this says, yeah, it says distillation. Oh, and it says distillation here. So we don't have to use reflux for these. Okay, I hope that makes sense for both of these. Next, if we're going to get, what we have to do now is look at the reduction of aldehydes and ketones using sodium borohydride or lithium aluminium hydride to reduce alcohols. Okay, so that's very straightforward as well. These are oxidations. Now we want to go back the other way. Okay, we did this in class, but it's all good to do it now. So let's start off now. If we start off with the ketone, there's my ketone. Okay, and now I want to reduce this. The two are up above were both oxidations, weren't they? So these were oxidations, these two. But now we're doing reductions. And these are these ones. So I'm going to reduce this. I give it two hydrogens. This is how we say hydrogen when we're getting it from the reducing agent. Getting from the reducing agent. Okay, and it reduces back to the secondary alcohol. This is a ketone, isn't it? I've done first. I should have done the aldehyde first. But we go back to the secondary alcohol. How do we do this? Well, generally we use sodium borohydride to do this. Okay. We could also use lithium aluminium hydride, but for this is a relatively easy reduction. So this is we use the sodium borohydride. Okay. Now, if I want to reduce an aldehyde, there's my aldehyde. I'm going to use the one I used before. This is propanal. I reduce it, get the hydrogens from the reducing agent. Again, I'm going to use sodium borohydride. And in this case, if I reduce an aldehyde, I end up with the primary alcohol. In this case, propan-1-R. Okay, so that's an oxidation and reduction. Okay, now interestingly, if you look at the carboxylic acid video, we can reduce a carboxylic acid all the way to a primary alcohol, but then we would use the lithium aluminium hydride. So for these quite simple reductions, we use sodium borohydride. We could use the other stuff, but we don't bother. The reason, let's have a look at this. Let's go into a tiny bit more detail. Sodium borohydride, the BH bond is stronger. It's stronger than in lithium aluminium hydride, where we have the ALH bond. Okay, this one is stronger, as I've just written twice, and this one is weaker. And that makes this guy, the lithium aluminium hydride, a better reducing agent because it gets rid of reducing agent because it supplies hydrogen more easily. Okay, so there you go. I hope that makes sense. Let me go up to the thing now, see what else we've done. Now we've done that as well. Now, this next bit, this is a bit confusing. So we're going to look at that bit later when we look at this bit. Okay. Now, we are going to come back to this in 5 minutes or so. Okay. But now we're going to look at the use of 2,4-DMPH. And this detects the presence of a carbonyl compound. Okay. So, whoopsie daisy, that's not right. There we are. Now we're going to use 2,4-dinitrophenyl hydrazine. Okay, and 2,4, and this is abbreviated to 2,4-DNPH. Okay, and what does this do? This is very straightforward. Don't worry about it. It looks complicated, but it's not. This tests for the presence of carbonyl compounds. Now, it doesn't differentiate. Okay, it could be an aldehyde or it could be a ketone. It doesn't tell me which one. It could be either. It could be this one or this one. So we don't know which one, but it gives us it tells us that there's either an aldehyde present or a ketone present. Okay, so it doesn't differentiate between these two. If we wanted to differentiate between these two, what we would use then, we'd use phthalins, which we did in class, or tolons. Okay, phthalins you would get blue to brick red. Tolons you'd end up with a silver mirror. And these are both positive tests. These are positive tests for aldehydes. Okay, so 2,4-DMPH doesn't differentiate between aldehydes and ketones. Okay, so let's have a look at it. All right, we have 2,4. Let's forget that. Let's have a look at the last bit of the molecule. We have this molecule. This is hydrazine. Okay, so hydrazine. Now that's this part here. Phenyl. That means there's a phenyl on my hydrazine. So get rid of one of the H's and put a phenyl group, which is one of these hexagonal things. That now is phenylhydrazine. Okay, now in organic chemistry, we number everything, as you know. So this carbon is called number 1, number 2, number 3, number 4, number 5, and number 6. We have 2 dinitros, 2 nitro groups. One is a number 2 and one is a number 4. So there's a nitro on number 2 and there's a nitro on number 4. So this molecule here is 2,4-DNPH. Okay, and there it is. It's a piece of cake. It's nothing nasty at all. All right. So what happens with this? Let's have a look at a ketone. Let me draw a nice ketone. There's a ketone. Okay, there's my CO, my carbonyl, and there's a ketone. And what this does is it gets attacked. Let me draw a different color. This guy here. There we go. This is my 2,4-DNPH. And there's a nitro on number 2, and a nitro on number 4. These react together when they're in solution. My aldehyde and my 2,4-DNPH, okay, and they'll crash together in a kind of a condensation reaction, and this will split off. So you can all see that that's water, okay. But what's the thing I get? I get this thing. There's my aldehyde thing. There was an aldehyde anyway. There's the CO and there's the H. And it bonds like that. It's quite weird, isn't it? There. And there's my phenyl ring. There's a nitro number 2, nitro number 4. And there you go. And we get this thing. And water. Okay. Now, if this were a ketone, how would I make this a ketone? Well, I'd replace this maybe with a CH3. And it's exactly the same reaction. The only difference is this would now be CH3. Okay, so it's exactly the same thing. Now, the interesting thing about this reaction, oh, there's a nice orange color. The precipitate, this comes out as a precipitate. It comes out of the solution as an orange precipitate. So this, the 2,4-DNPH test, If it is an aldehyde or if it's a ketone, we get an orange precipitate. So that's a test for an aldehyde or a ketone. Actually, it's a test for a carbonyl group. So if you get an orange precipitate, it's either an aldehyde or a ketone. Okay, and that's all we have to know about 2,4-D and pH. All right. So let me go up now. All right. Now we've done this bit. It's the presence. It doesn't tell you which one it is. It's either an aldehyde or a ketone. Okay. So we've done that one. Deduce the nature of an aldehyde or ketone of an unknown carbonyl compound from results of simple test. Failings and tolerance. We've done that, haven't we? Failings, it goes from blue to brick red. And tolerance, you get a silver mirror. Okay. Now, this is only the case for an aldehyde. So it tells you which one's the aldehyde, okay, rather than which one's the ketone. Well, you know which one's the ketone because it's the one that doesn't give a silver mirror, okay. Now, this last thing is a strange thing. This is a test we use on things, and it's relatively new in the AS syllabus. It's been there for ages in the A2. It's not hard, but it's just a bit odd for us, okay. And this is called the triiodoform test. All right. Or the iodoform test. This is what most people call it, the iodoform test. Now let's go a little bit of research into this. If you have a methane and the 3 of the hydrogens have been replaced by chlorines, we call this chloroform. Okay, if you have a methane and 3 of the hydrogens are replaced by bromines, we have bromoform. This is known as bromoform. And if we have a methane with 3 of the hydrogens replaced by iodines, we have iodoform. So this is basically, we're looking at this guy here. And this guy, iodoform, have I got the right colour on? Not quite, but near enough. This is a yellow precipitate when it forms. Okay. Now, this is a strange thing. Not strange, but it's an odd thing. The iodoform the iodoform test, it looks out, it searches for this group. Okay, that group. That's what it looks for. Okay, it's a strange looking thing, isn't it? But it's part of a molecule. Okay, and it's looking for that. Now, if this group is present in your molecule, all right, you will get a positive iodoform test. And how will you know that? Well, a positive iodoform test is a yellow precipitate. Okay, now, where do we get these things? Well, let's have a look at a few things that will give a positive test for it. There you go. This is going to be a positive test. Ethanol will give us a positive test. This will give a positive test. This is, what's this? This is butanone. Will give a positive test. Okay, let's move this up a bit. I'll show you what I mean by positive test in a minute. Propanol will give us a positive test. Oops, that's an H, isn't it? I'll talk about carboxylic acids. Yeah, let me put it over here for now. Carboxylic acids. This is a carboxylic acid. Doesn't give a positive test, but we'll come to that in a minute. Okay, and let's have a look at some weird thing here. Let's say I've got this. That will give a positive test. So what you've got to do is you've got to look specifically for this weird group here. Okay, this group here. Is it here? Yeah, it is here. Look at this. There it is. Is it here? Yeah, it's here. There it is. Could be a double bond or a single bond here. Doesn't matter. Is it here? Yeah, there it is. Is it here? Yes, it is there. Now, it looks like it's here, doesn't it, in the carboxylic acid, but the OH here modifies the functional group. So even though it looks like it should be here, it's not here. All right, we don't get them with carboxylic acids. All right. Now, I know it looks weird, doesn't it? But let's have a look at what's going on then Again, we don't really have to know this. We just have to know it gives a positive test. So I'm going to give something that's going to give a positive test. Have a look at this. There's my C. I'm going to do this. What is this for? Butanone. So this is butanone. Okay, and it's obviously going to give the positive test. Why? Because it's got that group I talked about. That group. Okay, it's got to have that group. All right. Now the pivotal thing is on this group. Let me get a nice red. It's got to have the CO group here. It could be a C double bond O or a C single bond O. It doesn't matter. But the CO group must be next to a methyl group. This methyl group is essential because this methyl group is going to fall off, and this methyl group is going to form my triiodo methane. Okay, now if you wanted a fancy word for triiodomethane, it's known as iodoform. Okay, but it's 3 iodines on a methane. And the big deal about this guy, how do we know it's formed? Because it's yellow. We get a yellow precipitate. Okay, it's a lovely yellow colour. All right, so that's it. What happens to the rest of the molecule? Well, crazy but true. This bit splits off, the CH3 splits off. But the rest of the molecule, this, turns to the corresponding carboxylic acid. Now, it's interesting, in A2, that's pretty ugly, isn't it? In A2, we use this as a reaction to make carboxylic acids. In AS, all you've got to know is if it's a positive thing, it has this funny group. Okay, so the corresponding carboxylic acid in this case is going to be propanoic acid. Propanoic acid. Okay, so you get, in this case, you get propanoic acid and triiodo methane. Okay, and as I say, this guy here is a yellow, even though I've just drawn it in orange. This is a yellow precipitate, and this is our carboxylic acid. All right, so that's what that does, but it's only this group, only the group I said above, this group here. Let me show you a negative, something that would give a negative test. Don't forget, it doesn't do it with carboxylic acids. Okay, everyone forgets the triodoform test, so it often comes up. It's very easy. All right, if I've got this, let me do this. CH3, CH2, CO, CH2, CH3. Now this guy, oh, my pen's a bit funny today. This guy is called pentanone, pentan 3-one, because I've got to tell you where the carbonyl group is. So this is number 3. Now this will not give a positive test monoform. Oops, that's not what I meant to do at all. Okay, this group, where I meant to do that one. This will not, even though, because it, oops, what's going on? Even though it looks as though we've got everything, we've got the CO, but the group it's attached to is not a methyl group, it's an ethyl group. And if this group is an ethyl group, it won't work. It only works if my carbon that's connected to an oxygen is next to a CH3. That is essential. Okay, just that. This can be any old rubbish here, all right, but this group has to be connected to a methyl group because, as I said before, the methyl group goes on to form my triodo, whatever it's called, triiodomethane. All right, and this is the iodoform test. Okay, now it works with aldehydes, it works with ketones. Let's do an aldehyde where it will work. There's an aldehyde. Oh, no, it's not. This is an aldehyde where it will work because you've got the CH3 next to the CO. This is a ketone where it will work. Okay, because you've got the C. There you go. It can work from either side there, can't it? So it'll work with this one, this aldehyde. It will work with this ketone. And even though we haven't done this yet, let's do an alcohol where this will work. Okay, ethanol will work. Okay, oops. And there you go. Ethanol will certainly work. So all of these will work. Why will they work? Because they have the magic group. They've got the CH3 next to a CO, CH3 next to a CO, CH3 next to a CO. They've all got the magic group. And if they've got the magic group, they'll give a positive test for the triiodoform test, all right, or the iodoform test. All right, I'm going to stop there now, and I'm going to do the mechanism that we missed out in the next video.